Hey guys, so for the rest of the school year, I think we'll just kind of pick up where we left off in Unit 7. Stuff isn't on your wasn't on your AP test, but it's still stuff that you were supposed to know for calculus, and so I'm not too sure where you guys are going to land whenever it comes to college and what they're going to expect you to know. So if they assumed you passed the test, they might assume you guys know this stuff. So what I'm going to do for this week is mainly we're just going to be focusing on catching up, reviewing what we learned in Unit 7 already. And then in the next following weeks after that, we'll throw on like a couple more lessons that would actually finish up what we were going to learn in Unit 7 anyway. So in our review, we're going to focus on three topics here. We're going to review area between two curves. We're going to review net change in particle problems. And we're also going to review rate in and rate out. And a lot of this stuff is going to require a graphing calculator. So if you don't have one, once again, I gave you guys lots of information on Google Classroom. It's probably still there on how to download free graphing calculators. And there's also free ones online you can get and whatnot. So, and yeah, all this stuff is still just extra credit. However, if you do plan on, continuing in math education next year, like if you're a junior, I would definitely do these lessons anyway. And if you are going into college and you expect that your AP credits are going to result in the fact that you don't have to take Calc Level 1, then I would still do these as well, because this is what the colleges are expecting you to know. All right, so all that being said, we'll go ahead and jump in here. So the first topic I want to talk about with you guys is finding area between two curves, okay? So here's the steps. You can take notes or not. It's totally up to you. I'm obviously not checking notes anymore. But this is pretty much the gist of it. You got to find where your two curves are crossing, okay? And what that usually requires is solving a system of equations, or sometimes our graphing calculator can do it for us. The next thing you're going to do is you're going to set up your integral. Now, the places where those graphs are crossing are going to be at 3 points here, A, B, and C. So they start crossing at A. Well, let me draw a picture here for you guys. So let's say I have a curve that looks like this, right? And another curve that looks like this. Well, this first point here, we'll call that A. This second point here, we'll call that B. And this third point here, we'll call that C. And you can find where they're crossing by solving a system of equations. And A, B, and C are just going to be the x values. You only need those when you're doing this. Now to set up your integral, it's always going to be the top function minus the bottom function. And from A to B would be from one intersection point to another. So this first one, for instance, would be showing me this area here. Now, by the time you get to the second part, if your graphs cross twice, which sometimes they do, if they don't, then we don't really need this part over here at all. You just need the first part. But if the graphs actually end up crossing twice like they do in my picture that I've drawn, and you're being asked to find this area also, then you need to set up a new integral, because now the functions have switched place. If I called this top one here f and this bottom one here g, then over here now g is the top function and f is the bottom function. So for this first one here, it would be f minus g, but for the second one here, it would be g minus f. If you don't do that, if you don't recognize which one is on top, then it's going to actually end up making this area come out to be negative, and it'll cancel the area out and you'll get a false answer. So we always want to have the one that's on top come first, because that way when we subtract it, we always end up with a positive outcome, so we get the areas, okay? And once again, we're going from B to C. Now, as you guys know, if you remember, the only difference between f minus g and g minus f is a sign. So for instance, just do numbers really quick. 3 minus 2 and 2 minus 3, they give you the same answer. It's just that one's positive, one's negative, right? And the way that if we're using a graphing calculator, you don't have to worry about this at all. You just have to put it in absolute value bars. It doesn't matter if you do f minus g or g minus f, because they're the same. And also, we don't have to break it up into two separate integrals. We can just start at A and end at C. So this is what you would do if you're doing it on a graphing calculator. But if you're doing it by hand, you do need to make sure you know which one's on top, which one's on bottom. You need to find all your intersection points and write up separate integrals. And we're going to be doing both of those today. Once you've got your integral set up, you're just going to go ahead and do the fundamental theorem of calculus, which we learned way back at the beginning of the year. So that's our beginning there, and we'll keep adding that. So that's topic 1. Let's go ahead and take a look at some example problems there. All right, so we have two functions, y equals x cubed plus x squared minus 5x, and then the other one is y equals x. Now, we want to find the area between these two functions by hand, so that's my first task. My first task is going to be doing it without a graphing calculator. So step 1 is to find where these graphs cross, and to do that, we need to solve a system of equations. So since the way you're going to do that is you're going to take the first function and make it equal the second function. So I have my first function is x cubed plus x squared minus 5x. My second one is x, so I just set them equal. Now at this point, what we're going to do is we're going to move everything over to one side. So I'm going to take this x off of this side. And at that point, to find where the lines are crossing, we're just going to solve a system of equations here. I'm sorry, we're going to use factoring to solve it. So the first thing you do when you're factoring is you always take out a greatest common factor if that's possible, which it is in this case. So I'm going to take an x out of everything. The next thing you're going to do is you're going to do the box method or the reverse FOIL method, whatever works for you on this trinomial here. Sometimes you get a difference of squares, and that's even easier. If you need help reviewing your factoring, I'm going to erase this soon, so if you want to get it before I erase it, but you put your first term here, you put your last term. I just realized I left a mistake here. That 6 should not have an x next to it anymore, so I just erased that. You put your last term here, and then you go ahead and find two things that make x squared, find two things that make 6, and you want to make sure that when you're all done filling in your box here, these two numbers should add up to make the middle number, which is 1x. They will if I make this 2 a negative, which is what we wanted anyway. So we have x minus 2 and x plus 3. And you set this equal to 0 and solve, so you get x equals 0. You set that equal to 0 and solve, you get 2. You set that equal to 0 and solve, and you get negative 3. So those are my 3 intersection points there. That's where these curves are intersecting. Okay. Now step 2 is we're going to go ahead and we're going to write out our integrals. So here we go. My first one, starting with my lowest x value, negative 3, is where they start crossing. After that, their next place where they cross is 0. So we go from negative 3 to 0. My next integral is going to pick up where that one left off at 0, and then it's going to end at the last cross point, which is 2. So there's that. Now for this first interval, from negative 3 to 0, I'm going to do function 1 minus function 2, but I don't know which one is on top. So we actually do need to figure that out. So how do you know which one's on top? Well, the first thing we're going to do is we're going to pick a point that's in the interval. So what do I mean by that? What I mean by that is pick a number between 0 and negative 3. So I'm just going to go ahead and pick negative 1. Okay? And then what you're going to do is plug it into each function. Okay? So let me tell you, I'll tell you why when we're done, but let's do that. So if you were to plug in 1 here to this, not 1, negative 1, I'm sorry. If you plug in negative 1 to this first function, you get negative 1. plus 1, so those cancel, plus 5. So you end up with 5. And if you plug in 1 to this other one, you just get 1. Now, as you guys can see, 5 is greater than 1. These are y values. When you plug in a number for x, you're finding a y value. So this function here, this first function has a y value of 5, and this second function here has a y value of 1. So since my first function has a greater y value, that means it's higher than this one. So for this first integral, it's going to be x cubed plus x squared minus 5x first because it had the higher y value. And then we do minus the other function. And by the way, it's probably a good idea to put those in parentheses. In this case, it really doesn't matter, but it will on the next one. So now, usually, just to be safe, you can do the same thing for the next one. You need to figure out which one's on top, okay? But it's almost unnecessary to do that. I'm going to do it just to be safe, but usually what's going to happen is whatever you had over here, it's going to be the reverse over here. So in other words, this one's going to look like this. I'm pretty sure of it. Every once in a while that won't happen, so it's worth checking just to be sure. But almost always it ends up just being the reverse. Okay, so let me go ahead and go through my strategy here again. Space for myself. They don't give me a very big eraser, so it takes me a little bit of time. Sorry about that. So now I'm going to pick a number between 0 and 2. That would be 1. So if I plug in 1 to the first function, I get 1. Plug in 1 here, I get 1. Plug in 1 here, I get negative 5. And if I put all those together, I end up with negative 3 for the y value of this first function. And if we plug in 1 to this other one, we get 1 for his y value. So in this case, we see that it is opposite this time. This time, this function gave me a bigger y value than this function, and therefore the x comes first. Now, the reason why it's not always going to happen is just because here's what happens. When two curves cross, right, they cross here, and when they cross again, they usually switch roles, right? However, it is possible. It is definitely possible for this to happen. You have them here, and then when they touch again, they actually touch like a tangent, and so they don't switch places. So that is possible. So it's worth checking just to be sure, but in general, they do just switch places. Anyway, so there's your setup. That's most of your calculus setup there. Now we're going to move on to the rest of it, which is what we learned way back at the beginning of the school year. We're just going to do the fundamental theorem of calculus to find the area for each piece. Okay. Now, for these problems, these are a pain in the butt, and there's tons of room for error. You have to just make sure that you are neat and pay attention to details so that you don't make mistakes. So step 1 is you want to go through and actually simplify first. So I'm going to do this minus x here. So negative 5x take away x is going to be negative 6x. And I didn't have my dx up there, just have space, but I'll put it in there now. And this other one, now this is something that you don't have to, this will always be true. Whatever you have here, the next one will be exactly the same, it's just all the signs will be opposite. So this one's going to be negative x cubed, negative x squared, and plus 6x. That will always be the case. Okay, so there's the simplified version. Now what we do after this is we're going to go ahead and integrate. So once you integrate, the integral symbol goes away and we replace it with brackets instead. And our numbers switch sides. We put the negative 3 and 0 on the right side now. 2 on that right side. And now we're going to integrate each piece. So we add 1 to the power and we divide by that number. Add 1 to the power and divide by that. Add 1 to the power. And if I divide -6 by 2, I end up with -3, so it's going to be -3x squared. And once again, you don't really need to go through a lot of mental effort for the next one. It's going to be exactly the same. It's just that all the signs are going to be opposite. So this one will be -x to the 4th over 4 minus x cubed over 3, and then plus 3x squared. Okay, now the next thing, we're going to do is we're going to go ahead and just plug in and evaluate. And this is where a lot of people start making a lot of boo-boos. You got to be neat and clean with your work. So I'm going to enlarge this because you'll see why we need to in a minute. We're going to have 2 sets of parentheses with a minus in between them for each set. And what we're going to be doing is we're just basically going to be plugging in these numbers here on the right side of the boxes. So I'm going to be plugging in 0 to all 3 of those. Now if I do, I get 0. So that's nice and easy. Then I'm going to be plugging in -3. That's going to be not nice and easy. So if I plug in -3 to this first fraction, I'm going to end up with 81 over 4. Plugging in -3 to the next one, I'm going to get -27 divided by 3 is -9. And then plugging in -3 to this last one here, I'm going to get +9 times -3 is -27. Okay? And then we're going to do the same thing in the other set. So we're going to be plugging in 2. That's going to be 16 over 4, which is -4. Plugging in here in the next one, I'm going to end up with -8/3. And then plugging in here, we're going to get 12, it looks like. And then plugging in 0, you got to love those zeros. It makes life easy. Just goes to 0 there. Okay, so once you've got that done, the next thing I'm going to advise you guys to do is distribute any negatives that you need to and get rid of all the parentheses. So the 0 we can ignore and distribute this negative. And so I'm going to end up with -81 over 4 plus 9 plus 27, and then plus -4 -8/3 plus 12. And we don't care about the 0. And this plus and negative doesn't really matter. I'm just going to change it to a minus. And there we have it. So now, at this point, I'm going to combine any terms that already have a common denominator. So this guy has nothing that it matches, so I'm just going to bring it down as is. And this guy has nothing that it matches, so I'm just going to bring him down the way he is. But all these other numbers have a common denominator of just being 1, right? So we have 9 and 27, that makes 36. Take away 4 is 32. Add 12. 32 plus 12 is 44, I believe. And then once you got that, you can go ahead and get a common denominator. So, some more space here. All right, the common denominator is 12. So I'm going to multiply this fraction here by a 3 on the top and the bottom. So times 3 times 3. And this one I multiply by 4 on the top and bottom, times 4 and 4. And then for this guy, we're going to need to multiply a 4, or 12 actually, on the top and bottom. That's going to be a pretty big number. Makes me worried, makes me wonder if I did something wrong. Okay, so we have 3 times 81 is -243 over 12, minus 32 over 12, and then 44 times 12. My goodness. Let's work it out and see what we get. 44 times 12. 528. That's not too bad. 528. Positive. And then after we've got a common denominator, we can just kind of put these fractions numerators together. So we have negative 243 minus 32 plus 528 all over 12. So I'm going to get out my trusty calculator here and put all the numbers together. So we have 243, which is negative, minus 32, and then plus 528. And I put 253. If you can reduce it, go ahead. I don't think 3 goes into this, though. Neither does 4. So I know that this can't be reduced, so we'll just leave it like that. And now we're going to have our drum roll moment. I'm going to bring up the answer and see if I got it right. I hope I did. A lot of work. Tons of places to make mistakes. Let's see. Yay, I did. Man, that almost never happens. Cool. You guys are like, and you're expecting me to do it? All right. Yeah, it's just being careful is all. It's not really a matter of expertise or knowledge. It's being careful, which I'm not always the best at. That's why I make mistakes. So here's one for you guys. If you want to, you can do it. You don't have to. This is just for you guys to practice. But go ahead and pause the video here, and when you unpause the video, you will see the solution. Okay, I'm going to show the answer here. So here it is. It looks like, yeah. You should, when you set these two equal, you should have gotten three values for x where they cross, -2, 0, and +2. Your first integral should have been the first x cubed plus x squared minus x squared, which would give you this. I forgot about the 4x. And then for the other one, it should have been x squared minus the x cubed. And when you guys were all done, you guys got a nice clean answer of 8 is what it should have been. So if you got this set up, I'm pretty happy. The only thing I want to make sure of is, did you guys remember to integrate? I get a lot of students who will start plugging the 0 in, for instance, here, and the -2 here. That's wrong. You should have integrated first and gotten this. And then you should have plugged in the numbers. I have students that constantly forget to do the integration. So my guess is that you guys, if you got past setting it up, which is my hope, if you didn't get the final answer, it's either because you forgot this, so take a note of that. Don't forget to integrate. Or maybe you just had some issues with fractions along the way. So I'm not too sure, but either way, you should have ended up with 8. All right, so now I'm going to show you guys the same problem now, but this time we're going to do it using a graphing calculator. Now, when you're using a graphing calculator, it is so much easier. Okay, I'm going to call this y1, and I'm going to call this one y2. Okay, so the setup is going to look like this then. We're just going to do y1 minus y2, and we're going to put absolute value bars on it. And my graphing calculator is going to help me know where they cross as well. So let me bring up my graphing calculator app here really quick. Okay, so here's my calculator. We're first of all going to be punching in our functions here. So we're going to push y1. So what was our first function? It was set to, it was -x cubed over 2 plus x squared plus 3x. Let's type that in first. Anytime you're doing, don't forget there's a difference between negative and minus. We're going to put the negative there. And anytime you're doing a fraction, you put it in parentheses. It's going to be x to the power of 3 divided by, I think it was 3, wasn't it? Nope, it was 2. And then we have x squared plus 3x. So there's our first one that we're going to enter. Then we go down to y2, and we type in the other function, which is negative x. Easy to remember, negative x. And then what we're going to do is we're going to graph this. And we can find where these lines are crossing. Now, because of the software I'm using, you can tell where they're crossing. It's going to be -2, 0, and 4. But I still want to go through the keystrokes because sometimes you end up with problems where they don't cross at nice points. So you want to know how to do it. Okay, so I'll show you how to do one, and then if you're kind of following along, you can practice it on the other one. But here's what you do: you push second, you push calc, and you're going to find intersect. So that's number 5, and you're going to basically just scroll the cursor to be where you want to find where they're crossing, and all you have to do is push enter 3 times. 1, 2, 3. So it's -2 for the x. Remember, we don't care about the y right now. And then we're going to repeat that process. So second, trace, 5, scroll over to the point you're interested in, enter 3 times, got your next one, and you can repeat it for the last one. But I already know it's going to be 4, so we don't need to do that. So coming back to this problem then, we now know that they are crossing at, they start crossing at -2, then they cross at 0 again, but since we're doing it on a calculator and we're using absolute value, we don't have to break this up into 2 separate integrals. We can just stop at the last one, which is here. And this is what I'm going to be typing into my graphing calculator to find the final answer. So much easier. Let's go ahead and do that. So let's push second and quit to go to the home screen. We're going to push math. We're going to click 9 for derivative. We're going to enter our first intersection point and our last intersection point. And we're going to put absolute value bars in here. So we want to push math. I want to come over here to number and click 1. And inside there, we're just going to put our 2 functions that we already typed into the y area. So we push variables. Scroll over to where it says y variables, push 1 for function, and we're going to do y1 minus y2. Keystrokes to find y2. And don't forget to come over here and push dx at the end as well, and enter, and you're good to go. There's our area under the curve. Much easier on a graphing calculator. Let's make sure we did it right. Hey, we did. All right. Now, here's one for you guys. I would practice this using your keystrokes. So go ahead and pause the video here, and when you're all done, I will show you the setup and the answer. And so here's your setup. It doesn't really matter which one you would call y1 and y2, but the cross points you should have found were the first cross point was 0, the last one was 3. We're going to put some absolute value bars around the 2 functions being subtracted, and then boom, calculate that in a calculator 10.542. Okay. Last thing I want to talk about for area between curves is doing integration with respect to y. Now, sometimes you want to find the area between curves, and those curves are defined not as functions of x, but as functions of y. Okay, now when we do that, it's basically the same thing. It's just that the difference is that you're going to have y values here instead of x values, and also your functions are functions of y, which means I'm going to put an x here instead. It's like x y. So it'll be x1 minus x2, and we're just going to go ahead and put it in parentheses now, and I mean absolute value bars. And don't forget, we're integrating with respect to y. So if you're using your graphing calculator, this would be your setup. Now, if you're not using a graphing calculator, you would still have to make 2 separate integrals, right? For the 3 points where they're crossing. And the difference is that instead of doing top minus bottom, it's right minus left. Okay, so what do I mean by that? Let me trace one of these really quick here in a different color. Well, first of all, notice the intersection points. That y value was 0. Let me erase my y's here and I'll plug them in. So this first y value here is 0. The next point where they cross is here, and that y value is 2. And the last y value they cross at is up here, that's up 4. So we start where we left off in the last one, and we end at 4. So there's that. Now we have two functions here. I've got this guy here, which kind of looks like a sideways parabola. And then we have this other one, which I'll just call the blue function, sideways cubic function. Now in our first interval here, from 0 to 2, the pink line is farther right than the blue line. So the quadratic function, the y squared plus 4y, that will come first, and this one would come second. But after they cross, now the blue one, the cubic function, is further to the right, so it'll be this function minus this one. So if you were setting this up, I'm going to call this 1, I'm going to call this 2. For the first one, x1 is farther to the right than x2. And for the other one, it reverses. Now, if you're doing this by hand, you'd do everything exactly the same, really. You would set these two things equal and you'd solve for y. That would tell you the 3 places where they're crossing. You would still have to plug in numbers on the intervals to find out which one gives you the biggest answer. The one that gives you the biggest answer is the one that's farthest right. So it's a lot like the other one. And then from there, you just do the integration like normal. Okay. But if you're doing the calculator, then once again here, our setup is going to be erased more than I wanted to here. You're going to start with your lowest y value to plug in, which was 0. And we end with our biggest intersection of the y values. Up here it's 4. And we don't really care about the order when we're doing on a calculator. We just put absolute value bars on it, and it takes care of it for us. So I'm going to be doing these by calculator just to kind of keep our time sweet. The only difference is that instead of integrating going from left to right, we're finding the area vertically by shading upward. Usually when you're finding area, you're shading left to right, but when you're doing it with respect to y, you're shading from bottom to top. That's it. So there's your difference in your setup. So at this point, I'll just go ahead and do it on a calculator really quick. Now here's the thing. Our calculator operates primarily as only x-valued functions. So we're just going to treat it like an x function. So in other words, anything up here that says y, I'm just going to pretend it's x. It doesn't matter. You get the same answer. So it's kind of repetitive at this point, but still I'll do it. For my first one, I'm going to type in negative x cubed over 2 plus 2y squared. Y squared. My other function is negative y squared plus 4y. Okay, I put that in wrong. Let me fix that. Not be there. And then I don't need to find the intersection points because since on this problem I gave you the graph, you can kind of tell what they are anyway. We're going from 0 to 4. So go ahead and type it in. We're going to push math. We're going to push 9. We're going from 0 to 4. and we're doing absolute value of y1 minus y2. And even though we're really doing this with respect to y, for our calculator, we're doing it with respect to x. Get your final answer there, which is 4. So, nice and simple, no big deal. For number 6, what I'd like you guys to do, see if you can do this, is I would encourage you to try and set this problem up. In 2 different ways. I would like you guys to, and you don't have to, once again, that's just your practice, but I would encourage you to try practicing it, setting it up, ready for the calculator. And then I'd also like you to set it up as though you were doing it by hand. Okay, so pause the video and see if you guys can at least set it up. And if you want to punch it into the calculator also, just for the heck of it, you can. When you unpause the video, you will see the answer. Okay, so first of all, let's see if I can fix it a little bit. Okay, so I was calling this one up here x2. So negative y squared was x2. And I was calling this other one here, the cubic one, x1. So it doesn't matter what order you put x1 and x2 in for the calculator, so long as you have your absolute value bars. Our starting y value is negative 2, and our ending y value of intersection is positive 2. If you're doing it by hand, we go from negative 2 to 0 first, and then we go from 0 to 2. So we have 2 separate area regions we're calculating. And for the first area region, the quadratic function, the one that looks like a U shape, is farther to the right than the blue one. So the x2, which is the quadratic, is farther to the right than the blue one, which is the cubic. So for the first one, from negative 2 to 0, it's x2 minus x1, and for the other one, it's x1 minus x2. And regardless of whether you're doing it by hand or in a calculator, you end up with an area of 8. Okay, and so that does it for our first topic, which is area between 2 curves. We're going to go ahead and move on into our next topic, which is accumulation functions. All right. Some of this wasn't too foreign to what we were actually doing as we were preparing for our test, but this is an accumulation function. This piece here is what we call the net change. Okay, notice these are capital F's, but this is a lowercase f. The derivative of the big F is the little f. So this one in here is the derivative of the big F. So when you integrate the derivative of little f, you get big F, right? What this represents basically is it represents how much the function has changed over time. So, for instance, we're going to be applying this a lot of the time to particle problems. So in this problem, what this first thing is going to be representing is it's going to be representing our final position, is what f of x represents. Okay, this is going to represent our starting position. So f of A is the first time value that they give us, and so f of A would represent your starting position. So big F represents position, and f of x is going to represent our final position, and f of A is going to represent our starting position. The lowercase f is the derivative of the position, and so the derivative of position is velocity. When you integrate velocity over time, it basically tells you the displacement, or how much the object's position has changed. On the interval a to x. So we'll see that kind of work out a little bit as we go on. But basically, this tells us if you know the velocity, from time 1 to time 2, if you integrate that velocity and plug in the time 1 and time 2, that'll tell you how much the object's position has changed over that time period. So if you take the change in position and you add that to the starting position, you'll end up with the final position, right? So for instance, suppose you started at position 1 and you added 12 to that. That's how much the position changed. Well, now the new position will be 13, right? You started at 1, you added 12, now you're at 13. So that's basically it. And so the key thing you want to pay attention to is that the little f is the derivative of the big F. The big F represents the position when you're talking about particles. The little f represents velocity. And this represents final, start, and change, net change. We call those accumulation functions because basically as you are changing, you're accumulating change, right, which is changing your final position. So net change, accumulation, basically the same thing. Now, when it comes to velocity problems, I'm going to say V represents velocity and X represents position. So X prime represents velocity then, right? I can write that up here if this helps. X is position. So in other words, this is a function where if you plug in a number, it will tell you the object's position at that time. And when you take the derivative of that, you get the velocity function, which is where if you plug in a number, it will tell you the object's velocity at any given time. Now, whenever you integrate the velocity, you get the net change, right? But when you're talking about moving objects, what we call the net change is displacement. And what displacement is it tells you how far away you are from your starting place. Okay, so for instance, let's say we're on a line here and I start off at x equals 1. And let's say the object was traveling, it went this way, and then it bounced back this way, and it finally stopped here at about, let's say, 5. Well, the displacement is how far away the object is at its final point from its starting point. So the displacement in this case would be a positive 4 because it's 4 spaces to the right. Now, if I were to keep going this way and ended up at negative 3, then the displacement would still be 4, but this time it would be negative 4 because it's to the left. Okay, so displacement, the integral of your velocity, tells you how far you are from your starting point. So if you know your starting point, you can just add this number to it, and you can end up with the final position, right? So you have your displacement plus your start equals your final, okay, which is what this is down here. Now, if you take the absolute value of your velocity, what that does is it doesn't take into account direction anymore. It doesn't take into account whether you're going right or left. It just puts it distance only. So now, instead of telling you how far you are from your starting place, it tells you how much distance total you traveled. So I mean, let's say we went out up here to 10, right? So if I'm going from 1 to 10, that's 9. And then if I go all the way back to negative 3, that's 13. And so my total distance would be 9 plus 13, which is 22. So while the displacement would be negative 4 for that, because I land at negative 3, the distance would be 22. And that's what happens whenever you take the absolute value of velocity. Since it gets rid of the signs, the directions, it just gives you the total distance traveled. Okay. And so this function here, the accumulation net change function I was showing you guys earlier, it's the same thing down here. It's just that instead of using big F and little f, I'm using X and V to represent particles, or moving objects. So if you integrate the velocity of a moving object and add it to its starting position, you will find its final position. That's basically what that is. So we're going to go ahead and take a look at some problems and apply this stuff now. So this is the 2003 FRQ, question 2, which means that it's a calculator problem. Part C is asking us to, and that's all I'm going to do. I'm not going to do A or B or D right now. I'm just going to be looking at the stuff that we just talked about. So it says, find the total distance traveled by the particle from t equals 0 to t equals 3. So in the beginning of the problem, it tells us that we have a particle moving along the x-axis, and this represents its velocity. They also tell us that its starting position is x equals 1. Now they just want to know what is the total distance traveled by this particle. So let's do that first. So the distance traveled by this particle is going to be the absolute value of its velocity. And we're going from 0 to 3. And that's all we have to do. I'm going to calculate it too, but that's it. That problem is done once we calculate it. So I'm going to go ahead and get out my calculator here real quick. So the first thing we're going to do is going to go to y equals, and we're going to type in our function, negative t plus 1. And then it's going to be sine of t squared divided by 2, I believe it was. All right, then we're going to go back to the home screen here, and we're just going to push math 9. We're going to put in our limits there. We're going from 0 to 3, and we are going to be doing the absolute value of that. So it's going to be math, number, absolute value. Then we're going to put in y1 by pushing variables, scrolling over to y variables, function, and y1, the velocity function that we had, and then finally the x, enter. And so we end up with 4.333, 4.334 if you're rounding to the thousandths place. And that would be the distance traveled by that particle. Okay. Now I'm going to go ahead and add my own question here. I'll call it E. My question for this is going to be, find the position at t equals 3. Now I want to find the object's position at t equals 3. So for this particular problem, I'm going to let x of t represent position. Okay, so x of 3, the position of this object, is going to be equal to its starting position at t equals 0 plus its displacement from 0 to 3. And that will tell me where the object lands. This piece here will tell me how far away from its starting point the object is after 3 seconds. The velocity integrated from 0 to 3. It gives me the displacement, how far away it is from its starting position. And this is its starting position. So if I add its change in position to its starting position, I can end up with where it actually lands at, which is x3. And once again, I'm just going to be handling this on my calculator. So let's go ahead and jump back to our graphing calculator. I've already got all the same stuff typed in. So at this point, we need to plug in x of 0. Now, coming back to this, x of 0 is given to us in the problem. They tell us that the object's starting position is 1. So this is just equal to 1. So what I'm going to be typing into my calculator is 1 plus this. And that will tell me the answer I'm looking for. So here we go. 1 plus the integral from 0 to 3. This time we're not doing absolute value because we're doing displacement. We're not doing distance. So we're just going to put the y function in there now. Without absolute value. And that'll tell us where the object lands. So after 3 seconds, the object was at 1, but now it's at negative 1.197. Round to the thousandths place. Okay, so that's that. So I'm going to do another example. This one is going to be, instead of using a graphing calculator, though, we're going to be looking at this without a graphing calculator, and also we're going to be looking at it from the perspective of graphs rather than equations. But you'll find that a lot of the setup is pretty much the same. So before I answer, there's only one question on here that I'm actually going to do. It's part B. But before I do part B, I want to do another one. I'll call it part E again. But before I do it, let's read what we have. So we have a particle moving along the x-axis so that its velocity at time t on the interval from 0 to 6 is given by the differential function v, whose graph is given above. This is a graph of the object's velocity. So as you guys can see, from 0 to 3, the object has a negative velocity, which means on this interval it's moving to the left. And from 3 to 5, it's moving to the right. And then from 5 to 6, it's moving left again. So that's our velocity function there. So what else does it tell us? It says the velocity is 0 at 0, 3, and 5, which we already knew. And the graph has horizontal tangents at 1. I don't think that's going to be really relevant to our problem that I'm going to be working on. It also has a horizontal tangent here. I don't think that's going to be used for us. Now the next part is the area of the regions bounded by the t-axis in the graph of v from 0 to 3, 3 to 5, 5 to 6, or 8, 3, and 2. So from here to here is 8. We're going to call it negative 8 though because it's below the curve. This one is 3. And then from 5 to 6 it's 2, but it's negative because it's underneath the curve. Okay, so they didn't tell us what the signs are. We just have to know they told us the areas, and we have to know that they're negative areas because they're below the curve. So there's our setup. Now, let me go ahead and throw a question at you. Oh, one more thing. The starting position is negative 2. So what if I were to ask you guys, what is the distance traveled on the interval from 0 to 6? Okay, well, don't let the newness of this problem throw you. We already know how to set up distance, right? It's from 0 to 6, and it's the absolute value of the velocity. Now, here's where things do get a little bit different. You have to remember this. What is the integral of a function? Well, the integral of a function is just its area under the curve, which we know. The areas are negative 8, 3, and negative 2. But remember, it's absolute value. So at this point, we don't care if they're negative areas or not. So on the interval from 0 to 3, it traveled a distance of 8. And then from 3 to 5, it traveled a distance of 3. And then from 5 to 6, it traveled a distance of 2 for a grand total of a distance of 13. So it's actually easier, but you just have to remember how to transition your thinking here. So integrals, when you're thinking of graphs, is area. And since we're doing distance, which is absolute value, you neglect the signs. Now, let's do a different question. I'll call it F. Let's suppose that, let me put these back really quick here. All right. Let's say I asked you, what is the object's position at x equals 6? Or I guess I should say t equals 6, not x. Well, the position at x equals 6 is equal to its starting position plus its displacement on the interval from 0 to 6. And displacement is just the integral of velocity. Now, what is our starting position? They tell us it's negative 2. So this first piece here is negative 2. That's the starting position. And this piece here, once again, that's area under the curve, right? But notice it's not absolute value this time. So we actually keep the signs of the areas it gave us. So it's negative 8. So it moves 8 spaces to the left. And then 3. So then on the interval from 3 to 5, it moves 3 spaces to the right. And then for the last interval from 5 to 6, it moves 2 spaces to the left again. So my object starts at negative 2. And this is all of the displacement that occurred. So if we just combine all those, it'll tell us my final position. So it started at negative 2, then it went 8 spaces to the left, 3 spaces to the right, and then 2 spaces to the left, which means now we are at position -9 if you add all those. Okay, so displacement, you keep the signs as they are given to you, but with distance, you take the absolute value. Okay, so there's that. Now we're kind of in a better place to answer this question B here. It says, for how many values of t on the interval from 0 to 6 is the particle at x equals -8? Explain your reasoning. Well, let's see here. At t equals 0, my position is -2. And by the time I get to t equals 3, my object has moved 8 spaces to the left. So if I go 8 spaces to the left, that's going to put me at -10, right? And then by the time I get to t equals 5, my object has now moved 3 spaces to the right. So if I add 3 to that, I end up at -7. And then finally, on my last interval from 5 to 6, the distance it moves, the displacement is -2, so it moves 2 spaces to the left again, putting me at -9, which was we got for our last answer there. Now the question that this one is asking us is for how many values of t is the particle at -8? Well, this is an IVT question. If you're going from -2 to -10, and then from -10 to -7, and then from -7 to -9, how many times are you crossing a position of x equals -8? Well, from here to here you would have to, right? If you're going from -2 to -10, you would have to cross -8 to get there. And then if you're going from -10 to -7, you're going to have to cross it again. And then if you're going from -7 to -9, you have to cross it again. So there, the answer to this question is 3 times. So x equals -8 3 times on the interval from 0 to 6. Since it's continuous and goes from -2 to 10. I did not write that well. Let me back up. -2 to 10. And -10 to -7. And -7 to -9. So for each interval, it crosses -8. Okay, I'm wording my IVT a little bit differently there. We could have really worded it in the more formal way that I've taught you guys earlier. I think since our test is done, we can kind of lax up on it a little bit. But I mean, technically what you could say is you could say, since x goes from -2 to 10 on the interval from 0 to 3, and the function is continuous, there must be some point on that interval where x equals -8. So you can get a little bit more specific, but here I'm just using a little bit more of a common sense general speak. Our test up a bit. But anyway, there it is. So that's position functions there with accumulation. I'm not going to be including any student practices in the notes for these, but I am going to be assigning you guys some homework problems. But all these homework problems are going to be FRQ questions that are already done. You guys know you can look up answers in videos to get some practice if you need it. I'm going to move into our last topic now, which is net change. So let's take a look at net. Not net change. I'm sorry. Rate in and rate out. All right. So how rate in and rate out questions work is basically like, let's pretend like we have a bathtub here, right? Here's my bathtub, little ghetto bathtub I'm making here. And we usually have a faucet, and that faucet is pouring water into the tub, right? And that's causing my level of water in the tub to change, right? But we also have a drain in the tub. And so the drain can let water out also, right? So we have a rate at which water is coming into the tub, and we have a rate at which water is leaving the tub. So I'm going to let I represent the rate in and O represent the rate out. So we're going to say that this is rate in. Okay. Now usually this is measured in some. In this case, I'll just stick with the water example here. Let's say that it's liters per minute. Let's just say it's liters per minute. Okay, or units. Now that's the rate in. Now when you integrate a rate, that tells you the net change. So if you're integrating your rate in from A to B, what that's telling you is how much the amount of water in the tub is changed on the interval from A to B. So now when you do this, I'm letting x represent time. So my input variable is x. And when you integrate, it's kind of like you're multiplying your rate function, which is I of x, by a time. I of x times d of x. So my units for rate in are liters per minute. If I multiply that by dx, which is a x variable, right? That's time only. The times cancel and we're just left with meters. So that's something we talked about in preparation for our test, so hopefully that's not too foreign to you. The point here, though, is that when you integrate, you multiply a time unit. And so this is going to be the amount of water added on the interval from A to B. And the units would be liters, right? Not liters per minute, but liters. Now, I'm going to let O represent the rate out. How much water is leaving this bathtub. And that's also going to be in liters per minute. And when you integrate this, this is the amount of water lost on the interval from A to B. And its units are still in liters. So basically, we have rate in and rate out. When you integrate it, it tells you the net change in the amount. Okay. Now, I'm going to let T of x, which is going to be I minus O, that's just going to represent your total rate. So we have a rate at which water is being added to the tub, and we have a rate at which it's being taken out. So if we do I minus O, that's going to tell us the rate of change. So for instance, if the rate in is greater than the rate out, if this number is bigger than this number, then you end up with a positive number, right? And that means the amount of water in your tub is increasing. But if your rate out is bigger than your rate in, then you're going to end up with a negative answer here when you subtract them. And that means that the water level in the tub is decreasing. Okay, so that just tells you the total rate of change. So we have the rate in, we have the rate out, and we have the total rate once you combine them together. Now when you integrate this, this tells you the change in the amount of water over time. And our time is from A to B, right? So this integral here, it doesn't tell us how much was lost, it doesn't tell us how much was added, but rather it puts those together. You take how much was added and you subtract from it how much was lost. That just tells you overall how much did the amount of water in your bathtub change over time. Now we could take this concept of rate in and rate out, and we can combine that with the accumulation functions we talked about earlier. So this piece here matches what we had up here, right? Which is the total change in the amount of water in the tub. Well, if this represents the starting amount of water, this represents the change in the amount of water in the tub, that'll tell us the final amount of water in the tub. So we can combine the concepts of rate in and rate out with accumulation functions that we talked about earlier. Now I left a column over here just for the heck of it. Something that might help you on some FRQs. I might throw a few questions in on this. But just so you know that if you have a rate in and you take the derivative of your rate in, Well, that takes and it divides the rate in, which is liters per minute, it divides it by a time factor, so it becomes liters per minute squared. And what that basically tells you is that it tells you how fast the rate is changing, the rate of change of water is changing. So for instance, let's say that you know, for some reason you're a weirdo and as your tub is pouring water in, you're very slowly turning the knob so that the water's coming in at a faster and faster rate. Well, this number here will tell you just how fast the rate at which water is coming into the tub is changing. So it's the rate of change of the rate of change. Or let's just say that you have a bunch of kids' spongy toys floating in your bathtub, and as the water is draining out, more and more of these spongy things are clogging more and more. So that's going to change the rate at which the water is leaving. So O prime of t will tell you how fast that rate is changing, and that will also be in liters per minute squared. Anytime you take a derivative, you divide by a time unit. So there's that. So it's possible to take derivatives of your rates in and your rates out. And just remember that if you take the derivative of a rate, you're dividing by a time unit. And all it tells you is how fast your rates are changing, because rates change also. All right, so we're ready to jump in and try an FRQ on something. Okay, so I'm going to do, as an example here, 2005, question 2. It's another calculator problem. The first 2 or 3 questions are usually calculator questions on the FRQ. Obviously, that didn't apply this year because of the thing we had going on. But let's go ahead and take a look at our problem here. I'm going to actually start by just talking about some extra stuff, and then we'll maybe address some of these questions as we go along, okay? But I just want to make sure you guys have the basics down, and then maybe I'll plow through some of these questions. Let's take a look. The tide removes sand from Sandy Point Beach at a rate modeled by this function, and a pumping station adds sand to the beach at a rate modeled by this function. So this here is our rate out. R represents the rate out, and S represents the rate in. So we have sand that's being taken away, and we have sand that's being added to the beach. They also tell us here the units. The units are cubic yards per hour for these things here. They also tell us that the time interval 0 to 6, and they tell us that the starting amount at t equals 0 is 25 cubic yards of sand. All right. So before I begin answering the problem, though, I just want to interpret all of our stuff here. So this is our rate out, and it's in cubic yards per hour. And this is our rate in of sand, and that's in cubic yards per hour as well. Now, what does it tell me if I integrate R? Well, R represents my rate out in cubic yards per hour, but if I integrate that, that's going to multiply the time factor, and it's going to give me cubic yards. And so what it's going to tell me is the amount of sand removed over whatever time interval we're looking at. I'll just put A to B for now. It just tells us how much sand was removed, and that's going to be in cubic yards. Okay? And the integral of S of t tells us how much sand is added. In cubic yard. So R tells me how fast sand is being removed, but the integral of R tells me how much was removed over time. S tells me how fast sand is being added, but the integral of S tells me how much was added. Okay? So now this is kind of important. If I want to find the total rate of change, so I'm just going to make up my own variable. I'm going to use the same one I had on my worksheet earlier. Let's say t represents the total rate of change. It's going to be the rate in minus the rate out. So the order that you put these in matters. It's the rate in first, which is S, minus the rate out. It has to be minus rate out because that's how much is leaving. So that's the one that's being subtracted. And this tells you your total rate of change. So we have sand coming into the beach, we have sand leaving the beach, and if you combine those, that tells you how fast that the amount of sand on the beach is changing overall. Now, since that's just another rate, that's also going to be cubic yards per hour like the other rates are. Okay. Now, if we integrate T, then that's going to tell us something else still. That's going to tell us the change in the amount of sand on the beach. Instead of putting the integral of T, though, I'll put the integral of S minus R, which is the same thing. But if you do that, that's going to tell you the change in the amount of sand on the beach on any given time interval, A to B. So it'll just tell you what the total change was. So you had a total amount removed by integrating the R. You had a total amount added by integrating the S, and by subtracting those, that tells you what the total change in the amount of sand was on that time interval. Okay, and then one final equation I want to write, and in case you guys haven't noticed what I'm doing, I'm just putting all the equations that I had up on the last slide there when I was introducing this. The last thing I'm going to put is this. I'm going to let y of t represent the amount of sand on the beach at any given time t. The amount of sand on the beach at any given time t is given by the starting amount of sand on the beach plus the total change in the amount of sand on the beach for any given time interval. We're starting at 0 and we're ending at whatever t we want to. And I'm just going to put S and R. Save. So I've got 1, 2, 3, 4, 5, and then 6, and then 7 different equations up here that all represent different things, okay? And once again, I'm just kind of hearkening back to this little worksheet that I gave you guys earlier. Rate in, rate out, the integrals, total, integral of that, and then the accumulation function. So I just basically took this problem and applied all of those to this problem. So, and interpreted it in each of those contexts. So now that we have this, it might help us answer these questions a little bit better. Now, for my purposes, I'm going to go ahead and erase all this because I don't have enough space on here to write everything. But, you know, you guys can take a screenshot of it or pause the video and write down some notes if you want, and that'll help us. These will all help us understand a little bit better about how to answer the questions that are coming up. All right, so the first question is asking us, how much sand will the tide remove from the beach during the 6-hour period? Well, we're only talking about removing it, and they want to know how much is being removed. Well, this is how fast it's being removed, but if I want to find out how much was removed on the interval from 0 to 6, the 6-hour time period, I'm going to integrate the rate at which it's being removed. And from there, you're just going to punch that into your calculator, and it's going to tell you the answer. But you don't want to forget to include your units. We talked about how the integral of R is going to be cubic yards. Okay? I think I'm going to go ahead and skip the calculator work if you don't mind, just to kind of save myself some time and space here. I don't want to bore you guys too much. But there's that. Let's go ahead and take a look at the next one here. Part B. Write an expression for y of t, the total amount of sand on the beach at any given time. Well, I actually already did that. I said y of t is equal to the starting amount plus the integral from 0 to t of s minus r dt. Now, the only thing that you could maybe do a little bit different is we know the starting amount of sand. They told us in the beginning of the problem that it starts with 2,500 cubic yards. So that would be the answer to part B. They actually don't want you to plug anything in at all there. They just want the formula. All right, let's go ahead and take a look at another one here. Find the rate at which the total amount of sand on the beach is changing at t equals 4. Okay, so this, as we already said, represents the total amount of sand on the beach at any given time, right? So if I wanted to take the derivative of this is going to go away. And the derivative of an integral is just going to leave me with the s function minus the r function. And that's what I called earlier. I just called that t of x, remember. It just tells you the total rate at which the amount of sand on the beach is changing at any given time. So on your calculators then, they want to know what is the rate of change of the total amount of sand on the beach at t equals 4. So basically you're just going to plug in 4 to s and r and subtract those values. And once again, you would just type those functions into your calculator and do it on your own. Okay. So you see how easy this is once you take a minute and just kind of take the rate in and rate out that they give you and apply this worksheet here to it to kind of interpret everything before you begin. It takes a lot of time. I don't know if I'd encourage it if you're actually doing it on an AP exam, but it could be helpful for your homework this week. Kind of makes the question easy to answer. Now for part D, this is kind of a toughie, but we'll go ahead and delve into it a little bit. And then after that, I think we've covered a sufficient amount of information. I'm going to go ahead and set you guys loose on trying some, but I'll do part D just to kind of show you. It's kind of like taking the stuff that we talked about today and combining it with old stuff that we've already learned. So for the interval from 0 to 6, at what time t is the amount of sand on the beach a minimum? Well, I'm trying to find the minimum value of the amount of sand on the beach. Well, we've already found a function for that, right? The function was y of t is equal to the starting amount plus the integral from 0 to t of s minus r, right? Now I want to find the minimum value. Well, let's switch gears now. We've been talking for quite a while about reviewing some new stuff that we haven't seen in a while. Or sorry, old stuff that we haven't seen in a while. Well, let's think back to our AP review sessions. How do you find a minimum? Well, you do the candidates test, right? So we need time and we need a total amount. Why? Okay, we're starting at 0 and ending 6, so you do your beginning amount, your ending amount. You also need to find places where the critical values are. How do you find critical values? Well, you find y prime of t, which we already did in one of the other problems anyway, and we found it was this. And you set it equal to 0. Now, if I set this equal to 0, then that means I can add r of t on both sides, and I can just say s of t equals r of t. So what I'm going to be doing then is on my calculator, I'm going to graph the function s of t and r of t, and I'm going to find where they cross. That will tell me where they're equal. Because when the rate in is equal to the rate out, that means the total rate of change will be 0, which will give me my critical values. Once I know my critical values, I can just plug each of them in up here to find the amounts at each time, and that will tell me the minimum. Okay, so let's go ahead and I will go ahead and pull out my calculator here and do it this time. Let me type in these functions real quick. So I went ahead and typed these in. Notice how I've typed them in. You want to make sure your parentheses around the 1 plus 3 there and your fraction as well. Now I'm going to go ahead and push graph. And anywhere where the rate in is equal to the rate out on our time interval that we care about here is going to be a critical value. I'm wondering if they cross here at all. I'm not sure. It doesn't look like it, but I definitely know they're crossing here. And we're only going from 1 to 6. I'm going to adjust my window. I'm only going to look at the interval from 0 to 6 because I don't want to find things I don't need to. So let's look at the graph. So yeah, so here's 0, here's 6. They do cross right there, so that would be a critical value. And I don't think they're crossing here. it doesn't look like it. So I'm only going to find this one over here. So we're going to go to second, calc, intersect. And I'm going to scroll over to where they're crossing. And I'll push enter 3 times. And it's 5.117. Now you can write that down, or the way I taught you guys is you can teach your calculator to store that value. When you're on the graphing screen, the first thing you do is you push enter, and then you push store, and then alpha A, I guess is what we'll store it under. Ah, darn it, it didn't work. That's how mine works, I think. Let me go back to my graph. I'm going to do this again really quick. Let me pause my video. Okay, I found out what was wrong. I had to push enter twice before I pushed store. I'm not too sure why this version does that, but it does. Anyway, so now I'm going to push alpha A, and it will store that as my answer. That will store it as A on my calculator. So now we're ready to answer the question here. So that's where the graphs are crossing, right? So if I wanted to come back to my original equation here, we know where they're crossing. There's only one critical value. So it was, I've already forgotten, 5.118. So let's review. First, once again, we're trying to find when is the amount of sand a minimum. This function represents the amount of sand. If you want to find a minimum, you do candidates test, which means you put your start and end point as well as critical values. Critical values are where the derivative of your function equals 0. And since this was equal to 0, another way of looking at it is when is the rate in equal to the rate out. And to find the answer to that, I found the place where my graphs crossed on the graphing calculator. So now that I've gone that far, I just need to find out what the y value is for each of these. Now this first one's pretty easy. They're just asking us what is the amount of sand at time 0. Well, they tell us that it's 2,500. So we're good there. Now for these other two, though, we're going to have to plug it into this expression here. Okay, so let's go back to our calculator and we have y0, which is 2,500, plus the integral from 0 to, my first one I want to plug in is where they cross, so that's 5.118. So I'm going to push up, and I'm going to push alpha A. So I'm putting in the A there, and we're doing the rate in minus the rate out. Now on my calculator, rate in was my second one I plugged in, so I'm going to go to y variables. I'm going to push y2. Oops. Out of there real quick. All right, variables, go over to y's, push 1 for function, push 2 for y2, minus y1. And that's dx. There it is. So that's the amount of sand on the beach by t equals 5.118, because that's what A represents. So I've got 249.2. Round it to the nearest whole number. Once again, on the actual test, you wouldn't want to do that. You'd want to get 3 decimal places. We're easing up. Our test time's over. So let's repeat this again. Only now we're going to do it for t equals 6. So instead of typing all this again, you can just push second and enter, and it will put all that function back in there for you again. And all you need to do is scroll back to the one number we want to change. I want to change it from A to 6 now, and enter. And that'll tell me that now we're at 2493. So what's the absolute minimum amount of sand on the beach at any given time on 0 to 6? It's this. So we would say the minimum value is 2,492 cubic yards, the amount of sand on the beach. Okay, and my justification is just basically the candidates test here. Now, even though I didn't use my calculator to solve a lot of these, I mean, I could show you like number 1, that's what we would have got. Number 2, we had that. Part C, I didn't actually solve it, but I did set it up. Would have been that. And then we got the right answer here, 2492 cubic yards at t equals 5.117. So, once again, so long as you have the basics of rate in, rate out, and how to integrate them and get total amounts, you're going to be good. I might throw in a few extra types of funky questions for you guys to mess around with, but you can always YouTube the answers and look them up and learn how to do them. If we get a chance, I'll try to do a test on all this stuff with you guys, but I don't know if we'll have a chance before the year's over. But anyway, so that's our review. That's everything we talked about in Unit 7 just before we left for break. We are done with review, and then next week we'll actually kind of head into some new stuff. So, see you guys then.